Welcome to Basic Mathematical Analysis class. Today too we will have a discussion on properly divergent sequences. So it's a continuation of your last class. In the last class we have seen if xn is a sequence of real numbers and we will say that xn tends to plus or minus infinity and we will write limit of xn equal to plus infinity if for every alpha belongs to or there exists a natural number k of alpha such that n greater than or equal to k of alpha, then xn is greater than alpha. So similarly, for negative infinity also we have seen. And we will say that the sequence is properly divergent in case we have either limit xn equal to positive infinity or limit xn equal to minus infinity. And we have seen, see here, the thing has to be noted here is that when you're saying this minus infinity and plus infinity, this infinity just denote a symbol, or it is just stands for a symbol sake. It's not a number. Okay, so it should be noted here that the infinity, when I am saying, it is just a symbol. And the last class we have seen the theorem, a monotone sequence of real number is properly divergent if and only if it is unbounded. And a comparison test too we have studied, that is if xn and yn be two sequences of real numbers and suppose that xn is less than or equal to yn for all n belongs to n. If limit of xn is positive infinity, then limit of yn is positive infinity, and if limit of yn is negative infinity, then limit of xn is minus infinity. See, this is given as xn less than or equal to yn for all n is given. That means, suppose you are having a sequence. Suppose you have got the sequence as x1, x2, x3, etc., xn, etc. And suppose you have got a sequence y1, y2, y3, etc., ym plus 1, etc., yn, etc. Now suppose for every xn less than or equal to yn is not true, but after certain stage, see after this stage, that is the stage is going to be n plus some k. So after this stage, whatever is coming here xn, here yn, we can compare. That means we will get xn is less than or equal to yn for every n greater than or equal to n plus k. So this stage onwards, this condition is holding, means then also this theorem is valid. Can you follow? So after a particular stage, here is given that xn less than or equal to yn for all n belongs to n. Even if this is not the case, but after a certain stage we are getting this inequality, then also we can apply this theorem. So we will note that here it has a remark. Theorem 3.614 remains true if condition 1 is ultimately true. Ultimately true means, that is, if there exists a m belongs to n such that xn less than or equal to yn for all n greater than or equal to m. So after a particular stage, when you are getting your xn values are less than or equal to yn, then again you can use this theorem. Now if condition of 1 hold and if limit of yn equal to infinity, so what is given? So this is the condition. It's given that xn less than or equal to yn is given, right? Then suppose your limit of yn equal to positive infinity. which does not imply that limit of xn is positive infinity. Can you follow? Limit of yn equal to positive infinity does not imply the limit of xn equal to positive infinity. Similarly, if limit of xn equal to minus infinity does not imply limit of yn equal to minus infinity. Okay, so that we will note it here. If limit of yn equal to positive infinity, it does not follow that limit of xn equal to infinity. Similarly, if limit of xn equal to infinity does not imply the limit of yn equal to minus infinity. So that means this theorem cannot be reversible. That is, whenever xn less than or equal to yn and limit of xn equal to positive infinity, then limit of yn is positive infinity. Then limit of yn equal to positive infinity does not imply limit of xn equal to positive infinity. In the same way, if xn less than or equal to yn for all n, then limit of xn equal to minus infinity cannot guarantee that limit of yn equal to minus infinity. That is the remark B. Now we will have a theorem, limit comparison theorem. So I have said that the condition for converging or properly diverging sequences condition, then whenever a sequence is a monotone sequence, if it is not bounded, then it diverges. Now all the sequences whatever given is cannot be a monotone sequences and all. So we want to check whether a non-monotone sequence which is going to be convergent or diverges or properly diverges. We want to check. For that, we can make use this theorem. This theorem says that let xn and yn be two sequences of positive real numbers, and suppose that for some L belongs to R, comma L greater than 0, we have limit of xn by yn. So whenever defining xn by yn cannot be 0, right? So yn cannot be 0, that is equal to L. Then limit of xn equal to positive infinity if and only if limit of yn equal to positive infinity. So I will mark this as a star mark, and let us see how we can prove it. So if star holds, if our equation star holds, so before that it should be noted that so limit of yn cannot be equal to 0, and moreover yn not equal to 0 for every n. These two should be understood here. Then only we can define xn by yn and limit of xn by yn. Okay. So if star holds, there exists some k belongs to n such that 1 by 2 into L is less than xn by yn, which is less than 3 by 2 into L. Since this given that limit of xn by yn is L, right? Then xn by yn, you take the limit in these sides, you will get 1 by 2 into L is less than limit of xn by yn less than 3 by 2 into L. Limit of that is 1 L by 2 is less than L less than 3 by 2 into L, right? 3 by 2 is a quantity greater than 1. So this is valid. So we are making use it here. Then what for you are making it here? Since we want to get this is a constant sequence. You can consider this as a constant sequence. and you can compare it, right? For all n greater than or equal to some k, which implies 1 by 2 into L into yn is less than xn less than 3 by 2 into L into yn. This is possible since I have taken my yn is not equal to 0 for every n. So this is less than yn for all n greater than or equal to k. Now consider the first part. Consider the first part of this, that is this one. Now consider 1 by 2L into yn, which is less than xn for all n greater than or equal to k. Greater than or equal to k. Now if we want to say that limit of xn equal to positive infinity if and only if limit of yn equal to positive infinity. So we will assume that first of all limit of yn is positive infinity, then we want to say that limit of xn is also positive infinity, right? So we have got this inequality here. Now if limit of yn equal to positive infinity, then what will happen? Then by theorem 3.6.4, what was that? 3.6.4, this one. If xn is positive infinity, then yn is also positive infinity wherever xn is less than yn. So you can compare it here. Here 1 by 2 L into yn is less than xn. Now if this sequence converges to positive infinity, then by this theorem xn is also converges to positive infinity. Then by theorem we get xn also converges to positive infinity. Now from star, now we want to assume that xn converges, right? Star limit of xn by yn is equal to L, which implies limit of xn equal to L into limit of yn, right? It's given L not equal to 0 and L not equal to infinity also, not equal to infinity. Therefore as your xn tends to positive infinity, what will happen? This side is L into limit of yn, that is L not equal to 0 and L not equal to infinity. So whenever your xn tends to positive infinity, what you are getting is then your yn also tends to positive infinity, right? So we have proved that whenever the sequence limit of xn by yn equal to L, then limit of xn equal to positive infinity if and only if limit of yn equal to positive infinity. So with this, I am winding up that session here. Thank you for your patient listening. Thank you. The next class we will have some problems. Okay, thank you.